our listeners can actually get your keynote from Monday on YouTube, so they can go watch that. But for people that aren't able to go and watch it, in broad strokes, what did you talk about? What was the thrust of your keynote?
I spoke about the impact of and use of nanoparticles for treatment of immune responses. Two types of areas were covered. On the one side, we elucidated the use of nanoparticles for drug delivery to improve immune response against cancer. And then the second part of the talk was going exactly the opposite way, and that is the use of nanoparticles to turn off the immune system in the case of people with autoimmune and serious allergic disorders.
Wow. So for the layman, how do you describe a nanomaterial? What's the criterion by which something is or isn't a nanomaterial?
The classical definition of a nanomaterial is something in the size range of between 1 to 100 nanometers, that at least one of its dimensions perform to that size. But we've learned over time that the size is only one of the characteristics of nanomaterials, that actually its functional performance is of importance, so that size barrier of 1 to 100 nanometer is something that is not strictly adhered to in terms of the functional use of nanotechnology.
Okay. And what types of things do you guys get up to with these nanomaterials?
Well, if you talk about the work that we do in my group, two broad areas. The one is to look at nanomaterials from the perspective of, are they safe, and what are their properties that could lead to potential hazard generation. That's the traditional point from where my work in nano began with. That aspect was based on the fact that we studied the impact of air pollution on lung disease and asthma, and became aware of the impact of very small nanoparticles in the air that's emitted by, for instance, diesel engines or vehicular emissions. And so that then was what attracted me to the world of nano, and we then used those studies to also begin to look at a whole range of different nanomaterials. So once into the domain of studying the nanomaterial effects on biology and health, I also then became interested not on just the implications of nanotechnology, but also applications. And so as an allergist and an immunologist, one of the areas that attracted us was disease processes such as cancer, inflammation, and then started developing nanomaterials to impact, disease and pathology in those areas.
What kinds of things are nanomaterials used to do in tissues, so in treatment situations? Well,
basically everything can be done. Nanomaterials can have a huge application basis for impacting biology and medicine. I would say that if I have to summarize what the effect of nanomaterials is from a biological perspective, is that you can use an engineered approach to medicine through the use of nanomaterials in ways that were not possible until the advent of nanotechnology. And examples of that include, for instance, getting medicines, drugs to go past barriers that normally is impenetrable or very difficult to get to. And a classical example is, for instance, drug delivery to the site of cancer.
I see.
Where nanomaterials can improve the delivery of chemotherapeutic agents, as an example, in levels and quantities that is more than what the free drug can do.
I see.
But if you expand on that, the applications can then include areas that are very difficult to get medicines to, such as the brain, and going drug delivery past the blood-brain barrier. I'm not involved in those studies. And then other examples of what nanomaterials can do is, other than getting access in an engineered way, is also that nanomaterials can be used as containers, so they can include medicines, drugs. You can use nanomaterials as imaging agents to view, visualize disease processes.
Wow.
And then nanomaterials can also be used to construct small biosensors that can, tell you about the state of biology and health in the body.
So what is it about the properties of these nanomaterials that allow them to pass through these barriers, as you say, and I guess carrying with them drugs that are working in a more targeted way? Like, how does that work?
So the basic principles is, number one, that you begin with size of a small object. The size of a small object is deliberately designed to specifications of an access site to the particular tissue that you want to get in is an important commodity, but size is not enough.
Right.
Beyond that, you then have to make the material so that it is biocompatible, very, very important. You can address the surface of the material, which is a very important commodity, that at the architecture between tissues and nanomaterials, there is a sort of a communication. We also call that, science-wise, a nanobio interface.
Okay.
And then you can go beyond that to the size of a nanomaterial and what form or shape it is. Could have important aspects on biology. You can decorate the surface of the nanomaterial with what we call targeting ligands. And those would be commodities that would then take the nanoparticle to a desired site of interaction. Other design features of nanomaterials is to any nanoparticle that enters the body. The body has a big defense mechanism for the liver and the spleen to want to remove those materials.
Yeah.
And by putting certain moieties on the surface of the nanoparticle, you can actually retard that process of rapid removal by the liver and the spleen, and then control the amount of time that nanomaterials can circulate.
Right.
And so what I'm spoken about now is, what nanomaterials on their own can do, but also nanomaterials can be used dynamically in terms of many different converging technologies. That if you use a nanomaterial plus another commodity, for instance, you can use nanomaterial plus irradiation, or you can use a nanomaterial plus certain light wavelengths to do functions, such as the nanomaterial comes in, it uses all its nanoproperties for engaging the nanobio interface, and then you provide physical chemical stimuli. For instance, to have a nanoparticle open a control valve to let the content out, or let the nanoparticle generate heat locally at a tissue site, which can be used, as a treatment commodity.
What are the ethical considerations? You talked a little bit about that being part of your work too. So what are the ethical considerations of introducing engineered materials into what eventually would be human tissue?
Well, nanotechnology as a whole, has important applications and implications. Okay? And those implications, very important, because we not only introduce them into humans, but at the manufacturing place, right? You get occupational exposures. Once the materials go out into consumer products, those consumer products have a typical life cycle, where ultimately they can decompose.
Mm-hmm.
So the ethical considerations should also include the environment.
Mm-hmm.
And that's a two-edged sword. Number one is you don't want to contaminate the environment with a nanoparticle that could be dangerous.
Right.
On the other side, you can use nanomaterials very effectively for environmental remediation. When we get to the side of, therapeutics and the use of nanomaterials in nanomedicine, important considerations there for developing any material that will go into the clinic or into the patient are all the considerations that we have in the U.S. that is under the revision and control of the FDA, is to make sure that that nanomaterial is safe and effective, that it is safe from the perspective of not causing additional adverse effects. And so, classical examples of what is required as primary entry point is, number one, is that the material is degradable. You do not want to have nanomaterials stick around. You want them to perform their function and then exit the body. The second is that the nanomaterial can be made reproducible because, nanomaterials have one nanoparticle, have many different properties. And in order to meander through the body and perform the functions, you want to make sure that the properties of that material is rigorously controlled so that the results can be reproducible. You want to make sure that the material per se, with or without the drug, is tested so that the nanoparticle, before you introduce its active pharmaceutical content or cargo, is safe, and that it is also safe after you introduce the cargo. A lot of considerations goes into, because it's a new technology, we started out with a lot of excitement about what nano can do, but that excitement have to be controlled as we move along in order to make sure that everything that is done safely. So there is a huge ethical dimension.
Right. If, current constraints were freed in terms of, the physics or the chemistry of using nanomaterials, sort of what next big leaps do you see in this space?
The big leaps that is occurring for nanotechnology as a whole, as a part of a series of converging technologies, is massive.
So it's happening, basically.
It basically is happening. Yeah. Is that at industrial scale, nano plus its converging technologies have become a $1 trillion industry worldwide.
Now. No kidding. So what sort of things are making up that industry? The things that make up that industry is material science, of which nanomaterials is an important part, plus all the other present-day technologies, IT, intelligence, etc. It's all a part. And so the biggest outlet of nanotechnology probably is in the area of consumer products that makes use of electronics, but it's very, very rapidly also contributing to the building of traffic, cars, aeroplanes, building materials, window planes, clothes. So the use potential for nanotechnology is unlimited. And so at the moment, there is in every aspect a tremendous growth in the introduction and use of nanotechnology. I think that the production and growth rate has been so fast that the ability to keep up with all the regulation
standard setting and safety is often under constraint. So far, fortunately, we've been very lucky that we've had no serious incidents of, a nanomaterial causing a widespread harm or damage. But the potential always remains there for any advanced technology, and therefore it needs to be watched.
Mm-hmm. I don't think that people realize you're citing that size of industry and that ubiquity. I don't think that people realize. I suppose what you're saying is that they're already coming into contact with nanomaterials.
Oh, absolutely. It's pervasive. You pick up your cell phone, its screen is made out of a nanomaterial. The computing ingredients in the nanomaterial, all its electronics are based on the properties of nanomaterials. The use of light, the applications also of just the cell phone in terms of all its remote sensing and communications, all of that is based on principles that includes a convergence of the use of nanomaterial plus other advanced technologies.
Wow. Then what other things do you see in the future? Because it sounds like you're talking about smart materials and drug delivery mechanisms and some other things. But what other future uses of this technology do you see coming?
I think the future use is unlimited in terms of its scope. I think that some of the interesting possibilities immediately ahead of us is the ability to use nanomaterials also to build quantum computers.
Oh wow! Okay.
Artificial intelligence in the field of medicine, the ability to use nanomaterial architecture surfaces to contribute to tissue engineering, regenerative medicine, the ability of nanomaterial to be used to control the immune system, the ability of nanomaterials to cross the blood-brain barrier for drug delivery and treatment of disease such as Alzheimer's. The ability of nanomaterials to play a huge role in therapies that are related to degenerative disease and aging through, various different commodities. The ability of nanomaterials to contribute to biosensors that can sense disease processes remotely, and then with the use of, for instance, a cell phone that is also, contains a lot of nanocomponents, to remotely broadcast this information so that you can actually have an input of health status to the doctor's office anywhere in the world.
This feels, from a layman's perspective, a bit like plastic 2.0, and I'm sure that there's some overlap in polymer and materials, nanomaterials. But is this another situation where we should proceed with caution, because these things, once out there, as a lot of polymer materials have gotten, are going to be a mixed result for humanity in a way?
Sure. So, if you that's in line of what I said earlier, is that you want to make sure that nanotechnology implications are considered and safely introduced. And so the example of plastics that you mentioned there is a question of, amongst others, life cycle analysis.
Right.
You make a material, and from cradle to grave, that material has a life cycle, and you therefore have to think through the contributions. You may, at the front end of it, get a lot of use and a lot of novelty, but at the back end of it, you also want to make sure that where that material is going to end up, that it does not cause harm to the environment. And the rate at which the technology is expanding at the moment in terms of not only the number of new substances, new materials coming forward, but the number of application uses puts a big constraint and emphasis to be able to look at all the possibilities across the board and before a material is being introduced. I think that to a large extent we've come to grips with the importance of doing preemptive analysis before materials are being developed. I think much more so than happened in the world of, say, chemicals, where 80 to 100,000 industrial chemicals were introduced over the course of decades, many of which were never assessed beforehand. And so as a result, there's a big backlog in the world of chemicals. For nanomaterials, the importance of safety, I think, was recognized within the first 5 years of this technology being developed. In fact, at UCLA, I received from NSF, one of the national centers, at an early stage, 2007, I think, to begin a comprehensive study about, what are the implications of nanomaterials on the environment. So I would say that this is the one technology in which the preemptive exploration of its safety has become part and parcel of developing the technology. But the technology is developing so fast that the backlog is always a possibility. As you will get materials that get out before they're properly assessed.
There's been a lot of talk in recent years about circular economies for materials and things. Do you foresee that nanomaterials will have a recyclable component? You talked about biodegradable, but is recycling something that you think would potentially happen in this?
Well, it's an interesting question. The answer is that it would be very important to consider that. If you consider electronic use, just some of the materials used in electronic containing certain metals and metal oxides, and their waste dumping have become a problem in some countries. Most of the nanomaterials we use in biology for nanomedicine are degradable. As I said, that is one of the early important. For materials that are non-degradable and can stick around, and especially stick around in the environment, that is important considerations that need to be given. And I do not think nanotechnology is mature enough at this stage to have contributed to a lot of materials at the end of their life cycle. But we have to consider that in 20 or 30 years' time. For instance, if you're going to build, many different building components now are being made out of, say, carbonaceous nanomaterials, is the consideration be given whether those materials, how they should be stored, how they should be dealt with, and what the possibilities are that we could have a waste dump of nanomaterials.
What led you into this field? I'm curious, since it's so new and so rapidly growing, it obviously didn't exist when you or I were in school. So how did this evolve as a career path for you?
So I mentioned this earlier on. As a career path for me, I'm a clinician. I treat people with allergies and immunology. I did a lot of basic research on pathways in the immune system that can cause disease, and so started understanding that. Then I arrived at a point in my career where I wanted my research to connect with what I do in the clinic.
Okay.
And so what I saw in the clinic were a lot of people with asthma, and in an inner city like Los Angeles, with in those days a much more polluted environment, you saw people whose asthma did not respond appropriately to standard medication. So it was clear that there are imprints from the environment that made a difference. And so I became interested, where I sat in my laboratory every day to see the smog or the fog come in to Los Angeles, and then I go to the clinic in the afternoon, and you see a lot of people whose disease on a bad day is worse and doesn't respond. So I decided, listen, I'll change my career track. I will start looking at the disease, and I will start looking at some of the molecular and chemical interests that I've developed. And so we began studying air pollution. And so with air pollution, we immediately opened up an area in which there was a lot of chemical data and physical data, but very few studies as to what it does in terms of biology.
Right.
And so we set up mobile laboratories all around Los Angeles, in which we did animals. We put in there and animal asthma models, and saw that, listen, yes, air pollution has an important impact, and air pollution comes in different size particles, and it was the vehicular emission, or the nanoparticles from vehicular sources, that had the most impact. And so the reason that I started seeing that nanomaterials from that perspective can have health effects. And so with the advent of nanotechnology in the 2000s, I was already in a place where I had begun from the side of something else.
Right.
Another man-made, a particle, inadvertent particle, the air pollution particle, that if we get to the advertent particles, that it would be important to consider their safety, and that's how we began.
And so you've seen quite an improvement, you think, in incidence rates of asthma? Like, has that been something that's improved, or small particulate matter? I know.
Well, so certainly air pollution standards and control have improved a great deal, and have had big health benefits to cardiovascular, respiratory disease.
Right.
In inner city environments such as Los Angeles.
Right.
And so the awareness of the importance for the control has clearly brought benefits.
Driven some policy change.
Right. So in US we call it the Clean Air Act.
Okay.
And with the benefits of the Clean Air Act is very, very clear in terms of the epidemiological studies that followed. For every small drop in the daily air pollutant count, the mortality rates go down in big cities. And if they jump up, mortality rates jump up 2 to 3 days later. And so the overall impact of the air regulations under the Clean Air Act has had a big impact.
Wow. That's very interesting. Well, thank you so much for joining us here. We appreciate it.
You're very welcome.